Perfect. We can begin.
So welcome to everybody again. Here we will have the first lecture by Guilherme Pimentel about cosmological fluctuations and the Bootstrap. So please go ahead, Guy.
All right, thanks. So the next couple of days, I will try to describe to you our current understanding of essentially the beginning of the universe and the origin of structure. And we'll try to convey a bit of some exciting new development that is essentially merging two apparently distinct areas of theoretical physics. One is the study of scattering amplitudes in flat space, and the other is the study of primordial cosmology, cosmological correlation functions. So usually I give similar lectures for people with a background in cosmology, given that I imagine that lots of people here come from holography, from the titles, and maybe, yeah. I will try to give it a more holographic flavor. You'll see that holography informs a lot of our intuition and understanding of how these things go. It's very similar, but on the other hand, there are important distinctions between thinking about holography and thinking about primordial cosmology. So in 3 hours, I'm very slow paced. So in 3 hours, we'll cover very little. So if you want to learn more, I taught online. So if you go to YouTube and you put my name, you'll find that there's some lectures I give at ICTP, which covers the basics of primordial cosmology. And also at GGI, 1 hour away from Pisa here, maybe right before the pandemic, early 2020. And early this year, if you put snow mass and these words here, I wrote 2 papers, one reviewing the progressing theory of primordial fluctuations, something we call cosmological bootstrap, and another one reviewing mostly the theoretical and observational aspects of the theory of initial conditions of the universe. So there's a lot of information, these papers, lots of references, and so on. This is just an excuse for me not to give any references throughout the lectures. So there are lots of references and citing properly who did what and when and so on in these papers. So as was emphasized in the introduction, I encourage you to ask many questions and interrupt me, because I'm still talking to, if I showed you the camera, I'm talking to an empty room here. But I wanted to give it in the blackboard to give you some sense of normalcy. Very good. So what is the backdrop? What is the motivation? So actually, so there are 3 lectures. So in the first lecture, I'll mostly motivate you, motivation, and maybe a bit of review of the basic observables. In primordial cosmology. Then the second lecture, I will become a bit technical and talk about this thing called the cosmological bootstrap, which is the idea of determining these cosmological observables by leveraging principles that we know and love, like unitarity, symmetry, and locality. So the observables that we're interested in, they're often so simple that if you ask a self-consistency question under some umbrella of assumptions, you can just classify all possibilities, okay? So this is a powerful idea, and it allows you to go much further than you would have if you just followed a standard textbook-like method to compute these observables. And the third lecture, I will talk about some unpublished work because it's really what's making me excited when I wake up these days, which is some connection between the calculation of these cosmological correlation functions and some nice mathematical theory of differential equations. Okay. So I will give it the mysterious title, differential equations for cosmological correlators. Hopefully by Wednesday, you'll become clear what I mean by it. So this will be almost philosophical. This will be slightly technical. This will be technical. But I hope that by here you'll be excited about, and it's just too beautiful. So I really want to tell you about it. Okay, so that's the plan. So let me start with the motivation. So we have a standard model of particle physics, and we also have a standard model that explains our universe at large scales, explains our cosmology, how the universe came to be, how structure formed, and the various eras that the universe went through, and so on. So the standard cosmological model is called lambda CDM, which stands for the cosmological constant lambda and the component of dark matter that we call cold. And actually, this is not the whole story. I'm sure you're familiar with this pie chart that shows the constituents of the universe, where like 80% dark energy, 70% dark energy, 25% dark matter, 5% ordinary matter. But it should really have an extra bit, the name. You also need special initial conditions to explain our universe, because if the universe was entirely homogeneous, like we're used to learn, like well described by the FLRW metric and so on, then we wouldn't be here. You need small inhomogeneities like potential wells and so on in order for structure to clump around those and then form stars, galaxies, etc. So not only we need a cosmological constant and dark matter and ordinary matter, we also need special initial conditions. So this plays, I would say it's a tripod. You need the three things working together. And the initial conditions at the level of our cosmological model, they correspond to 2 parameters out of 6. We need 6 numbers to describe the universe, and 2 of them come from the initial conditions. We call them AS and NS, and it has to do with the AS has to do with the overall, the typical size of a primordial seed, meaning how strong is the gravitational potential around the seed, and NS is a simple parametrization of the scale dependence, meaning if I have a seed over here, how likely it is to have a seed over there as a function of separation. Okay, so they are distributed randomly, but they're ordered in the statistical distribution of these seeds. So how does it work? How do we infer from observations these numbers? So unfortunately, I don't have color. So usually I draw this stuff in color, but bear with me. So here we are, us. We observe, galaxies and nebula structure. There's some scaffolding of dark matter that we can infer around which these galaxies clump. Then the universe is fairly boring for a long time. It's mostly neutral hydrogen as you go backwards in time. Okay. Then at some point, when the universe was quite young, it emitted this very hot plasma, the cosmic microwave background radiation. So here you observe the large-scale structure of the universe. Here you have this hot plasma, the cosmic microwave background radiation. And it looks randomly distributed, but you can ask statistical questions. So just like we're used to in quantum field theory, but here it's more at the level of ensemble average than quantum mechanical average, at least at the level of the observations. So here you can ask, for example, as a function of separation in the sky, or more technically as a function of wave number, what is the two-point function of the density contrast of galaxies? So there are lots of galaxies here. So I take a point in the sky, then I dial some separation in the sky, and as a function of separation, I multiply the amount of galaxies here times the amount of galaxies there, and that's a proxy of the density contrast. So you can ask this sort of question, the density contrast as a function of wave number, delta rho. And because of translation invariance, you expect wave numbers to correlate like so. And you get an interesting plot. It would seem like a random question to ask, but you get actually quite an interesting plot. The power goes up and then it goes down with some wiggles, etc. Okay. Maybe this is not so familiar, but now it's becoming a very important tool to infer cosmological information. Historically, most of our knowledge of the universe came actually from observations of its very, very early phase of the cosmic microwave background, where here you can ask similar type of statistical question, but because you're only measuring photons, it's different type of observable. You're measuring the fluctuations in the temperature. So there are hot spots, cold spots. So you measure the average temperature at a point, and you correlate with the average temperature around another point, another spot as a function of separation. But the CMB is emitted at roughly a very short period of time. So here it's really a snapshot. You don't really dial the depth. So technically what it means is that you think about the celestial sphere and you go to multiple. So you plot now as a function of multiple L, the temperature contrast, delta T, L. And this you probably have seen from the Planck satellite. So it starts fairly flat and then it has some big acoustic peaks, and then the peaks start getting damped. So there's some nice damping tail. And you can teach a whole course out of understanding these two plots, essentially, the relative heights of the peaks and the damping tail. And for us, what we care about really is this part here, the beginning. So of the plot. So from this, you can infer the amount of dark matter, the amount of dark energy, all sorts of cool stuff. From here, you infer the duration of matter domination, radiation domination, etc. And look, if you look here you're looking at very large scales, low multiples. So you're looking at very coarse grained features on the whole celestial sphere. And by this time, the universe is fairly young. It's around 380,000 years old, give or take. So, you can't run the clock backwards much longer. Here you hit the so-called Big Bang. By the way, can you see here or is the, yeah, you can. Big Bang. So you need initial conditions here that explain these correlations. Okay, so these correlations are really tracers of the distribution of structure in the universe. Now, if you look here, you see you're looking at such wide angular separation that the universe is just too young to have washed out any correlation that was imprinted here. So that gives you a hint that you need simpler initial conditions than this wiggly plot here at the beginning. And it turns out that you actually need super simple initial conditions. So if, let's see. If I look at the density, at the gravitational potential, the Newtonian potential phi, at the 2-point function of the Newtonian potential, right here at the hot Big Bang at the time equals 0, okay, as a function of wave number, and I multiplied this thing by k cubed to soak up some scaling that comes from the Fourier transform, you get essentially an almost flat curve. Okay, just a line with a very small tilt. And so this line here has very small scale dependence. So what it means is that you need very special correlated initial conditions right at the beginning of the universe. They are almost scale invariant, and the two numbers that I described to you here, that I mentioned to you here in the beginning, have to do with this last plot. So if I look at k here, k cubed phi, the height is given by AS, and the slope is related to NS. And these two numbers are measured. Okay. So for example, when we say that the cosmic microwave background radiation is fairly uniform with small temperature contrast of order 10 to the -5, meaning that the CMB, the difference in temperature between a hot and a cold spot is of 1 part in 100,000. It's really coming from the number AS. So AS is order 10 to the -10. Is this 10 to the -5 squared? It's squared because it's related to the size of the 2-point function. Okay, so it's the typical size of a temperature fluctuation. Okay, unfortunately, there is a concert here on the square tonight, so they're running a sound check at the moment. So if there will be noise, I can't control it. Sorry. The other number, NS, is also measured. It's very small tendency to deposit less power at short distances. So it has a very small slope, and it's also measured with a high significance. Okay, so these are measured, but of course they pose a huge puzzle, because it means that you need non-trivial correlations naively at time equals 0. So how can it be that you have a universe that has seeds, primordial seeds, sprinkled in such a nice, interesting pattern? It looks completely acausal. So it raises a puzzle, right? Acausal initial conditions. And the proposed resolution is actually to say that, hold on, this is not the beginning. There was some earlier phase of the universe. Now, what this earlier phase of the universe is a matter of debate. And I'll describe to you the leading paradigm, and honestly, the only paradigm in which I know how to do reliable calculations and predictions. Okay, so let's say the leading paradigm is that there was exponential expansion, accelerated expansion of the universe, and we call this thing cosmic inflation. Okay, so what does it mean at the level of our figure here? It means that what we call the Big Bang is not the beginning. There was some earlier era in which the universe undergoes accelerated expansion. So the patch of the sky that we observe was really tiny at the beginning of inflation, was really tiny, and got stretched to cosmological distances. But everything gets stretched, even quantum mechanical fluctuations. So if you think of like a little vacuum polarization diagram, you have a pair, then the pair produces energy out of the vacuum. It violates energy conservation, but that's okay for a short period of time because of delta E, delta T is order H bar. But now if you violate this energy conservation for a bit and the universe is expanding, actually this pair never manages to reannihilate, and then the particles get stretched and stretched and essentially go on the mass shell. So to draw a cartoon of what's going on, you have like some pair of particles that gets popped out of the vacuum, and then off they go their own way. They're stretched to very long distances, and then they generate some correlated, some EPR-like correlation at long distances between some chunk of energy here, a chunk of energy here. And that's why the gravitational potential becomes interesting and correlated. So the quantum fluctuations, despite the fact that the universe is stretching, the quantum fluctuations give a little bit of bumpiness to this initial surface for the hot Big Bang. And the bumpiness is correlated, okay, because they were at short distances earlier on. So that's the idea. And it turns out that the kinematics of the expanding universe is such that scale invariance is almost automatic. So hopefully that shouldn't be surprising to you, because it's very similar to what happens in ADS-CFT, in that you have a space-time of a cosmological constant, and then as you go to the asymptotic boundary of this space-time, you get correlation functions that enjoy scale invariance. It's just the way that the isometries of the maximally symmetric space-time are realized in some boundary, in some asymptotic boundary. The difference is that in ADS, the asymptotic boundary is spatial infinity, and here the asymptotic boundary is at at late times. So this is very cute because you see, in some sense, we infer the existence of inflation. It's really it's good to think about this problem in terms of holography, because we really only have access. We can only run the clock backwards with our standard model down to this time equals 0. Then all of this error of the expansion of the universe and so on has to be inferred indirectly from these observables. So these are, if you wish, this is the hologram, these are the asymptotic observables, and from this statistical distribution of these seeds, which is a static pattern, this is at equal time correlations, you need to infer consistent time evolution. Okay, so it's very similar to the spirit of holography. So we're going to use that as a guiding principle. So are there any questions about this part? No? Okay. So what are the observables? So here I'm gonna, again, contrast the type of question that we ask in different spacetimes as a function of cosmological constants, okay? So if I plot here the cosmological constant, here is 0. So at 0, if I draw some Penrose diagram, we have the Penrose diagram of flat space. And the type of question that is physically interesting is we set up some initial states, then you set up some particle experiment, the particles go, they interact in some interesting way, and then the particles away. and you have some detectors, and you measure some out states. Okay, so you're interested in the amplitude for these states to go into this state, and this is what the S matrix gives you. And the whole point of S matrix theory, of what people call on-shell methods, is to try to forget about what's happening inside of the Penrose diagram, if you wish. Now there's a whole field that has been developing recently, the people call celestial holography, which is trying to leverage this idea of asking questions that are intrinsic to this asymptotic boundary in order to reproduce what you would get from standard quantum field theoretic methods, say perturbation theory, to describe this process. Actually, even if you forget about holography, asking physical questions, like asking like some consistency question of like, if I set up some initial state and some final states, what is the possible amplitude consistent with unitarity, causality, and so on, is very powerful, because it often allows you to get to a final answer that is much simpler than the intermediate steps. So how do we go about solving this type of problems? We use the tools of quantum field theory. We write down a Lagrangian, we set up perturbation theory, we write down Feynman diagrams, and so on. But there are many examples, notably if you include particles with spin, in which, in order to achieve all of our goals of locality, symmetry, unitarity, and so on, you need to introduce a lot of extra baggage in the game. You need to introduce gauge redundancies, you need to introduce, even quantum fields themselves are not exactly observable. And then often you need to sum up a ton of Feynman diagrams to get an answer that looks very simple. So an obvious question is, well, could we get to the answer without having to go through all of these steps? So the steps give us firm footing, but given that the answer is so simple, it's natural to ask if there's another way. Let me give you an example of simplicity here. If you study amplitude, for example, of two gluons, okay, to scatter off into n other gluons, and you may look at their spins in such a way that these guys here, for example, have negative helicity, and then these guys here have all positive helicity. This is a famous story. Maybe you heard about this before. So some heroic computation was done in the 80s for this process at 3 level, okay, just 3 level, very simple perturbation theory. We know the Lagrangian, we know the Feynman rules. This is a theory of gluons, okay, so Young-Mills theory. And 2 guys called Park and Taylor computed this in the 2 to 4 process. It's like dozens of pages, the final formula, written in terms of redundant variables, polarization vectors, and so on. And then if you use some repackaging of momentum space, which it doesn't matter for us right now, dozens of pages of formula collapse to this answer here. 1, 2 to the 4th, 1, 2, 2, 3. So this is the answer. This bracket here is just some contraction between the 4 momenta of the particles, okay, with some number up front that is controlled by the Young-Mills coupling. So how can it be that you can estimate the number of Feynman diagrams grows factorially with the number of particles? Like hundreds of thousands of Feynman diagrams add up to such a simple formula, some rational function that is super simple. So how can it be? So this is another flavor of this idea of the bootstrap. there's maybe another question of self-consistency, that will allow you to bypass the usual machinery of Feynman diagrams. Okay? So there is holography, and holography is great and so on, but even at weak coupling, you can ask these self-consistency questions that are very useful. Okay, so this is an example at zero cosmological constant. A negative cosmological constant, then there is the usual story of this is what the Penrose diagram looks like. There's a anti-de Sitter space. And then the natural question that people ask is, for example, I have a hammer here. I have a little hammer. And I put some source here on the boundary, and then I measure, or some very far away, and then I measure some response. Okay. And then maybe the response is interesting and correlated. So I have some source J, and then I have some detectors here, O and O, and then I look at correlation functions of these responses. Okay. So this is typically encoded in the partition function as a function of the source. And then it gives me the correlation function of these responses. So correlation functions of the responses to excitations, boundary excitations, are the natural observable in ADS. And you probably know much more about this than I do, but you know, gives rise to the whole ADS CFT story. Finally, in cosmology, at the level of these cosmological correlators, so here we want to set up the initial conditions of the universe, this bumpy initial surface, and then we have this expanding space-time. So here we don't really control what happened in the past. So we know that, you know, we suspect that we start life at the vacuum. And then all we really control or measure are expectation values of quantum fields at this late time surface. So the natural observable here, we have the vacuum, maybe some interaction theory, and then we have something that, for example, measures the local curvature. We call this variable zeta, and we measure correlation functions of zeta at equal time, okay, which is this time equals 0. So you see, it's slightly different, the type of observable. We can correlate multiple of these. And if there is interesting correlation, it came from particle production at some point here during the expansion of the universe. And then there's this effect of space-time expanding that separates the particles one from the other. So notice that things are sort of similar, but not exactly the same. In flat space, we control the initial state, some particles, and the final state, some particles, we compute this overlap. In ADS, we switch on sources and we measure responses. Here in the Sitter space, you don't control the initial states, and you only measure late time correlations. And the correlations exist because earlier on there was some self-interaction or interaction mediated by other stuff, and off these particles go. Okay, so that's the idea. But the beautiful thing is that all of these things are connected to each other through analytic continuation. So if you take the formula, for example, if you take the formula of the cosmological correlator in the Sitter space, there is a way of taking some limits of that formula and reproducing some similar looking, say that there was some special dynamical process that gave rise to this correlation. There is a way of taking the formula in the Sitter space in cosmology and relating it to the same type of process in flat space. But then you can ask the question, well, what about in and out states and so on? Well, even in flat space, there is this notion of crossing. You can talk about particles of negative energy and so on. So even though it doesn't make sense physically, you can talk about a process of zero particles scattering into multiple particles, right? So that's the relation. So there is a way of connecting the physics of what's happening here to the physics of what's happening here. Likewise, there is a way of pulling this boundary very far away and focusing on a small box here and connecting the physics of what's happening in ADS to some flat space process. And finally, you can also try to analytically continue, if you wish, the cosmological constant to relate a process in ADS to a process in an expanding cosmology. So this is, I think this is very cool because it means that our partial understanding of physics in each of these arenas can inform some new developments in the other ones. And of course, here in flat space, we're way more advanced than we are in ADS. And in ADS, we are more advanced than we are in cosmology. So given that I come from the cosmology side, it's very useful to keep this in mind because I can try to import various lessons from these other fields or from these other observables into what I'm interested in. Okay. So these are the observables that one is typically interested in these other space-times and the one that we're interested in cosmology. So any questions?
Seems that there are no questions, but you have 3 minutes left, so.
Yes, I can see that. Okay, let me just finish by setting up our discussion tomorrow related to these observables. So how do these abstract discussion connects with what I told you in the beginning? So, or this thing here. So what we measure from the data is really the simplest possible process, which is just free field propagation or the 2-point function of a particle. We don't know what this particle is. All we really know is that it's probably a scalar. And we know that in order for the power to survive to late times, it must be very light in Hubble units. Okay, so that's all we really know. So to connect to these observables, the omega, the correlation function of the zeta variable, zeta, which is roughly the scale factor of the universe at different points, is related to this AS times k cubed is AS to the power k2 NS. Okay. There is some historically where we say that NS is a number close to 1 and we write k to the NS minus 1, but it doesn't matter. If you've never seen this before, it's k to a small number. Okay, this is not the NS that you'll find in the literature. But so what do you actually infer physics-wise from these two numbers? From this number here, you really measure the size of the 2-point function. So if you wish, the size of the wave function of this particle, the typical size. And from this number here, you measure the mass of the particle in Hubble units, which is the analog of the ADS radius for this period here, for this inflationary era. Okay. That I'm gonna say that is quasi de Sitter. Okay, so I'll put de Sitter in quotes. So this is all we really know. We just measure 2-point function of an almost free field in de Sitter space. So the obvious question, which is what I'm gonna talk about tomorrow, is what about higher point functions? What can you infer and how do you compute, say, a 3-point function? So what kind of physics does it encode, or a 4-point function of these particles? And can I connect to these observables and what we know about 3 and 4 particle scattering in space-times of other cosmological constants? Okay, so that's the That's the idea. We call these things known Gaussianities. Just because if you have 3 and 4 point statistics, then there's no weak theorem, right? So the 4-point function and the 3-point function are non-trivial. So it just means that the field theory that gave rise to these correlations is interacting. So it's a way, it's a method for us to learn about the intrinsic dynamics of what happened at the beginning of the universe. So I'll stop here. Tomorrow, I'm gonna refresh our memory of this discussion today, and I'll tell you a bit about how we go using these philosophical points that I made. How do we go about computing these non-Gaussianities?
Sorry, can I ask a question?
Yes.
Sure.